let's take a look at some more uh, diagrams. Um, Video sharing sites led by YouTube are popular destinations on the internet. Let's look at adult internet users 18 and over. About 27% of the internet users are 18 to 29s. Another 45% are 30 to 49s, and the remaining of them are old, like me, 50 and over. Um, the Pew Internet Life Project finds that 70% of the internet users that are at age have gone to video sharing sites. So let's say start taking a look at what this tree diagram could look like. First of all, we got our different age groups: 18 to 29, 30 to 49, and and 50 plus. And we basically said that this was 27%, this is 45%, and this is 28%. Now, amongst those, you could either be a video yes or a video no. And the video yes, so 70% of the young people are using video sharing sites. So I can go ahead and put those two branches of the table up there. There's video yes again, and here's video no again. And for the middle-aged people, it says 51%. So 0.15, and its complement 0.49. And then of the older people, it says 26% are video yes. And that means 74% are video no's. And there's our table. But we want to find out the unconditional probability of video yes. How might we do that? Well, the probability of video yes, let me make this a little bit bigger, could be thought of as the sum of the, I'll call them the event y, young, and yes, plus let's call these people the middle age people, probability of middle and yes. And let's call these people the olds, plus the probability of being old and yes. Or can I calculate these? Well, if I multiply 0.27 times 0.7, the probability of being young and being a video yes is 0.27 times 0.7, which ends up being 18.9. I did those calculations earlier. Probability of being middle-aged and a video yes, well, that's going to be 0.45 times 0.51. That ends up being about 0.2295. And then lastly, the probability of being old and a video yes ends up being 0.28 times 0.26. And again, I did this calculation earlier. It ends up being 1.1, or sorry, 0.0728. So if we add up those numbers, showing my work all the way through, I end up getting 0.4913. What's my conclusion? My conclusion is about 49.13% of all adults use video sharing sites. All righty, go on to the next page. A computer company makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers. The Texas factory makes 25%, and the remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70 and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to the stores. Suppose we select a computer at random from the distribution center. So let's make a tree diagram for this situation. Well, we have California, we've got Texas, and we've got New York. And the probability that a computer is made in California is 0.4, 0.25 for Texas, and for New York, 0.35. Now, it could be a laptop or it could be a desktop. And according to our narrative, 75% are laptops, which means that 25% are desktops. Laptop for Texas, 0.7. That means 0.30% for desktops. And for New York, half are laptops, half are desktops. Now, suppose we select a computer at random from the distribution. What's the probability that the computer is a laptop? Well, we can calculate the probability of California and laptop. And I'll write it out this one just for which is the probability that it's from California and the probability it's a laptop given that it's from California. 0.4 times 0.75. I do that calculation ahead of time, and that is 0.28. Probability of being from Texas and being a laptop, that's 0.25 times 0.7, which ends up being 0.245. That number doesn't look quite right. Let me double check that. 0.25 times 0.7. Okay, indeed, that number is wrong. That was 189, right? And then the probability that it's from New York and is a laptop is 0.35 times 0.5, and that should be 17 and a half. All right? So what's the probability of it being a laptop? Well, the probability that the computer is a laptop will be the probability that it's a California laptop plus the probability that it's a New York laptop plus the probability of it being, sorry, this is supposed to be a Texas laptop. And this last one is a New York laptop, which is 0.280 plus 1.89 plus 1 or 7, 1 or 0.189, 0.175. 9 plus 5 is a 4, carry the 1, 9, 17, 24, carry the 2, 2, 4, 5, 6. So it looks like about 64.4% are laptops. All right, move on to another idea. If two events are independent, then the probability of A and B can be thought of as the probability of A times the probability of B. This is the same idea that the probability of A and B is the probability of A times the probability of B given A. But since we know that B given A is equal to the probability of just B, just like it says there, that means this thing can get replaced with this probability of B. And that's the special multiplication rule for independent events. Very important stuff. On January 28th, 1986, the Space Shuttle Challenger exploded on takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets were to blame. Under the cold conditions that day, experts estimate the probability that an individual O-ring would function properly was 97.7%. But there were six of these O-rings, and all six had to function properly for the shuttle to launch safely. Assuming that they succeed or fail independently, find the probability that it would safely launch. All right. So the probability can be thought of as a 97.7% that the first O-ring did fine, and another 97.7% that the second O-ring went fine. And you can see that I would just get a chain of these. And when I finally got to here, the probability of all six doing fine ends up being 0.977 to the sixth power. Now, what number is that? 0.977 to the sixth power. It ends up being 86.97%. All right. Our conclusion, the shuttle had a 86.97% chance, not change, chance of launching properly. Okay. Now, please note, and this is going to be reinforced again, that means the probability of at least one O-ring failure was 1 minus this 89 or 8697, which ends up being 13.03%. Okay, so this at least one can always be thought of as 1 minus the probability that nothing bad happened, or none. There were no things that were wrong. That's a really high probability of failure, and it was a really, really sad day. So this idea of at least one has some really, really strange effects. First trimester screen is a non-invasive test given in the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New York Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive test. Let me, like I said, that even though everything is fine, 5%, they'll say positive that there is an abnormality. Among 100 people, 100 women with normal pregnancy, what is the probability there'll be at least one false positive? Now, again, the probability calculation here is that a single test being not positive is 0.95. So we can say, well, what's the probability that all 100 had negative results? Well, the probability of 100 negative results is 0.95 to the 100th power. And this is surprisingly 0.0059. Less than 1% of the time, they'll get 100 negative results, meaning 100 women all saying baby's normal when the baby really is normal. So what's the probability then of at least one false positive? Well, it's 1 minus the probability of all negatives, or 1 minus 0.0059, which ends up being 0.9941. A huge probability that there's going to be at least one false negative. Or sorry, false positive. All right. So how do we end up calculating conditional probabilities? Well, we already know from looking at the tree diagram, event A, event B, again, this is probability A, this is probability of B given A, that this gives us the probability of A and B. Well, if we start here with that known formula, and if we divide by the probability of A, then we get the conditional probability formula of that probability of B given A is equal to the probability of A and B divided by the probability of A. And that formula we're going to use right now. It says we classified 100 households having to do with their phone uses. What's the probability the random selected household has a landline with a landline, also has a cell phone? Probability that they have a cell phone given that they have a landline. See how it says amongst those with landlines. Well, the probability of a cell phone given that they have a landline is the probability of having a cell phone and a landline divided by the probability of having a landline. Well, the probability of having a cell phone and a landline, that's right there. It's 0.6. Probability of having a landline is 0.78. Doing that math, it ends up being 76.92. So you can see how we're using this formula to calculate that conditional probability. But you can also see how when we did other conditional probabilities, it's doing exactly what we did. Isolate the condition and then do your calculations only within that one line. Sometimes we use conditional probabilities to work backward. We had that example about the internet adult users and whether they use video sharing sites or not. Here's that complete tree diagram all done out. But this time we're going to ask a different question. What percent of the adult users who use video sharing sites are aged 18 to 29? Note, this number here is not that answer. This is the answer. What's the probability that they are a video yes, given that they are within the young age range? This question is reading, what's the probability that they're young, given that we know that they share video? So how are we going to do this calculation? Well, the probability of being young, given that you're a yes, well, that would have to be the probability of being young and video sharing divided by the probability of video sharing. Now, the probability of video sharing, now, first of all, this one's easy to calculate. It's right here, 0.1890. But the yeses are in these three groups. So the yeses are 0.189 plus 0.2295 plus 0.078. And if we go and put that into the calculator, we end up getting 0.3847. So again, the idea is here's a randomly selected person. I tell you that they share video, and you say, well, there's about a 38% chance, a 38% chance that they're young. Now, so with that calculation, about 38 point, let me change it to a percentage. About 38.47% who share a video site are young. Compare this to the probability that 27% in general adults share it. See how different those numbers are? That suggests that whether you share video and what age you are not independent. All right. That happens to be our last example. We learned a lot, but really big concepts about conditional probability and independence, some new formulas, and that concludes not only section 5.3, but it concludes all the lectures for chapter 5.